In this video, we will show an effect that's not even mentioned in most explanations for twin paradox. This is how Wikipedia explains twin paradox. The paradoxical aspect of the twins' situation arises from the fact that at any given moment the traveling twins' clock is running slow in the earthbound twins' inertial frame, but based on the relativity principle one could equally argue that the earthbound twins' clock is running slow in the traveling twins' inertial frame. In the space-time diagram here, drawn for the reference frame of the Earth-based twin, that twin's world line coincides with the vertical axis. His position is constant in space, moving only in time. On the first leg of the trip, the second twin moves to the right, and on the second leg, back to the left. Blue lines show the planes of simultaneity for the traveling twin during the first leg of the journey. Red lines, during the second leg. Just before turnaround, the traveling twin calculates the age of the Earth-based twin by measuring the interval along the vertical axis from the origin to the upper blue line. Just after turnaround, if he recalculates, he will measure the interval from the origin to the lower red line. In a sense, during the U-turn the plane of simultaneity jumps from blue to red and very quickly sweeps over a large segment of the world line of the Earth-based twin. When one transfers from the outgoing inertial frame to the incoming inertial frame there is a jump discontinuity in the age of the Earth-based twin. This diagram shows the age calculation made by the stationary twin. He calculates the traveling twin almost constantly ages slower than him during the journey. Only during brief acceleration and deceleration that the time dilation changes. At the end of the journey, he calculates that the traveling twin is younger. In this diagram, the same situation is presented with the simultaneity lines of the outgoing and incoming frame of reference. The traveling twin calculates the stationary twin constantly ages slower than him during outgoing journey. During brief turnaround, the stationary twin appears to age extremely faster. This forward time jump is shown by the faint blue arrow which indicates that it's seen from the perspective of the traveling twin. The stationary twin himself doesn't feel anything different that is caused by the turnaround event. During returning journey, the stationary twin appears to age slower again. At the end of the journey, he calculates that the stationary twin is older than him. The forward time jump appeared during the turnaround precisely compensate the discrepancy of calculation between the age of stationary twin and traveling twin. Now let's move our attention to the other side of the planes of simultaneity, at the right side of the diagram. Imagine there is a twin planet of the Earth, located twice as distant as the turning point of the traveling twin. This planet is stationary to the Earth at all time. The method shown previously to solve the paradox implicitly produce a side effect rarely mentioned elsewhere. The traveling twin predicted a forward time jump of stationary twin, shown by the planes of simultaneity on the left side of the turning point. On the right side, they indicate a reverse time jump of someone on the distant planet. It's necessary for that person to age the same as the stationary twin, since they stay in the same inertial reference frame. Now we will show how the reverse time jump can occur without introducing the distant planet. We will use two traveling twins instead. In this diagram, the first twin takes the journey just like the standard scenario of twin paradox. But the second twin doesn't stay on Earth. He also takes the journey symmetrically to the first twin, but in opposite direction. Both twins calculate the other twin ages slower than themselves during outgoing and incoming journey. But they also calculate the forward time jump of the other twin during their turnaround moment, which occurs symmetrically. At the end of the journey, they conclude that the other twin has the same age as themselves, still younger than the stay on Earth one. In this diagram, the second twin initially takes the same route as the first twin. But at midway, he returns to Earth. As soon as he gets back, he repeats the half journey, and meets the first twin at midway. They then return together to Earth. In this scenario, their calculation of each other's age at the end of the journey is similar to previous case. The forward time jumps precisely compensate for discrepancy by time dilation effect. Here is another scenario, starting the same as before. But the second twin continues his journey to the opposite direction after first return to Earth. At the end, they still have the same age. They have equal amount of time dilation, as well as forward time jump. Now the first half of the second twin's journey is reversed in direction. In this scenario, he turns around while not at the same location as the first twin, 3 times. The first twin only does it once. At his first as well as third turnaround, The second twin sees a forward time jump of the first twin. But at his second turnaround, the direction of the acceleration is away from the first twin. This causes him to see a reverse time jump of the first twin, indicated by purple arrow in the diagram. Consequently, the second twin will see the first twin to turn around twice. One occurs sometime before the reverse time jump, while the other is sometime after the reverse time jump. Some of you might say that it's impossible. Some say it's counterintuitive. Some other might say that it's just the consequence of the mathematical model used to explain the mechanism of symmetry breaking in twin paradox in the beginning of this video. I'd like to know what you think about this in the comment below.